So, Vesper theory, right? We have done this a lot. We did this last year. We learned about bonding domains. We learned about non-bonding domains. We learned about all these interesting molecular structures, tetrahedral, trigonal, planar, linear. We learned about how bonded and non-bonded domains deform those structures and turn them into things like bent structures and trigonal pyramid structures. We learned a lot about this. Well, guys, we're going to do a lot of that in review, with the understanding that you guys will write down every stinking bit of this. Even though you already know it, this could take a little while. But as you are writing down these things that are purely review and a complete waste of your time to write down, but again, you'll write it down anyway. Guys, along the way, we are going to stretch our understandings, because last year you learned that the octet rule was a hard and fast line drawn in the sand, and we don't cross it. Well, guys, today we're going to cross it, and we are going to talk about these elements in the third energy level and below that can exhibit a D sublevel, even though they're not there. Chlorine and even argon, sulfur, guys, don't have a D sublevel yet. But because they've started the third energy level, they can behave as if they do, and they can actually get the D sublevel involved in bonding. We'll talk more about how next week. But they can get the D sublevel involved in bonding, and now all of a sudden we got more room for electrons, and we can have 10 bonding domains, and even, or I'm sorry, 10 electrons, 5 bonding domains, and even 6 bonding domains, and we're going to talk about their names and their structures. So that's what we're doing today. Yeah. In the Ds. Yeah, so these elements, everything, well, really technically, so nothing before here can violate the octet rule. These guys are in the third energy level, but they don't violate the octet rule because they don't form covalent bonds. They're metals. These guys cannot violate the octet rule because they're in the second energy level, and the second energy level doesn't have a D sublevel. So it's not until you get into these dudes that they are non-metallic enough that they can form covalent bonds, but because they're in the D sublevel, or the third energy level, they can exhibit a D sublevel even though they haven't started to populate it. It's the potential for it is there. Go ahead. Yeah. Mm-hmm. Oh yeah, no. Well, so is there a way that you can tell which ones do this? And the answer is it's not like they're going to say, selenium, can this have more than an octet? But they would say selenium hexafluoride. What does it look like? And if you saw something like selenium hexafluoride, well, the fact that selenium's bonded to 6 fluorines tells you something's going on, right? And so that's what they'll do. They won't ask you to predict which ones can, but they would have you draw the Lewis dot structure for that, which we're going to do in a minute. So, yeah. Let's go ladies first. Go ahead.
Okay, I was wondering, does that only happen with non-metals?
Yeah, because this only happens with covalent bonding. And covalent bonds are only formed by the nonmetals. And the crazy weak metals like aluminum we talked about, but it's just the nonmetals. But yeah, you guys go ahead, Matt.
So there are no exceptions to the octet rule up until, because I feel like I remember about like boron.
Well, so boron does violate the octet rule, but boron actually violates the octet rule in the other direction. Yeah, so boron trichloride, which actually looks, so boron trichloride, which looks like that, exists, and it's very stable. But it doesn't have more than an octet, it has less than an octet. And it can do this, you can prove that it does this because you could also create a double bonded structure with this, but the formal charges become unfavored. And so this thing actually prefers to hang out like this, where boron only has 3 bonding domains and six electrons, and it is actually trigonal planar, and it just doesn't fulfill the octet rule in the other direction. Is that okay? You guys good? Let's do this. So guys, again, a lot of this is review. I would love it if you would give me a pass and allow us to not write down everything you already know, but in that spirit, here we go, Vesper theory. So guys, Vesper theory is the valence shell electron pair repulsion theory. Duh, Matt's writing it down.
I was just writing down the title.
Ah, okay.
I wrote down molecular structure.
Uh-huh. And guys, the valence shell electron pair repulsion theory all hinges on this idea of electron domains. So the idea is that these Lewis dot structures that we've been drawing are not flat, lifeless, two-dimensional structures. They're actually three-dimensional, and the reason they take on all these interesting three-dimensional shapes is because these valence shell electron pairs repel each other, and these things, these valence shell electron pairs we call domains, push on each other and cause these things to be three-dimensional. Now guys, you may remember that there are 4 things that count as electron domains: unbonded electrons, single bonds, double bonds, and triple bonds. You remember that? Okay, so all of these domains, which are just simply regions where electrons hang out, they push on each other, and as they push, they create these three-dimensional structures. Now guys, do you remember which one of these is biggest? The unbonded pair of electrons. And you may remember, ooh, we could even do this for triple bonds. You may remember the idea that this is all about the, to do this I've got to find 3 similar rubber bands. That'll work. Okay, so guys, the idea is that if the rubber bands represent the electron clouds, if you've got an unbonded pair of electrons, and my fingers are the nuclei, this unbonded pair of electrons is only being pulled on by one nucleus, and that makes these things short and fat. Whereas if you've got a bonded electron domain, it's being pulled on by 2 nuclei, and it stretches out and it becomes long and thin, and thereby less repulsive. And that just continues. So if you've got a double bond, we've got 2 of these things, but again, they both become long and thin. And if you've got a triple bond, never tried this before, you got a triple bond, they all become long and thin. So the most repulsive is the unbonded pair of electrons, because those electrons are centered around the nucleus, short and fat, and they push everything else away. You guys good? Okay. All right. So with this in mind, guys, let's take a little journey down memory lane, and let's talk about three-dimensional structures and the valence shell electron pair repulsion theory. Uh-oh. Hello? Oh, thank you.
The electron pairs that surround a central atom are most likely to be found in confined regions of space called electron domains.
Hey, and maybe we should mention this, guys. This idea of electron domains. This is something that is exclusive to this book. This idea of electron domains is actually a way of teaching Vesper theory that actually Eugene and his colleagues came up with. You will find it in other chemistry texts, but like that one that I gave you, the Zumdahl book, I don't think it's in there. All of that to say, guys, what you don't get to say electron domains on the AP test. They don't understand it because it's not a universal idea. So how are you going to get around that? I'll show you in a minute. It's actually a non-issue. But basically what I'm telling you is your brain is thinking electron domains, but you need a way to communicate that. And so I'm not saying abandon electron domains. It's just we got to be selective in terms of how we explain it. And we'll talk about that in a minute. Okay, so purple is nucleus. The little red guys are electrons, right? Here we go.
The electron pairs that surround a central atom are most likely to be found in confined regions of space called electron domains. The arrangements of the electron domains about a central atom are determined by the electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time they are held by their attraction for the central atom.
So guys, Vesper theory in a nutshell, right? Similar charges repel. Those are the electron domains. So the domains are trying to get near the nucleus and away from each other, and that's why they go 3D.
When there are two electron domains,
What do we call it? Two electron domains. Linear, what's the angle? 180.
about a central atom, they are located 180 degrees apart to minimize repulsions. Three
electron domains, what do we call it? Trigonal planar, what's the angles? 120.
domains about the central atom take up positions in a plane separated by 120 degrees. Four electron
What do we call it? Tetrahedral. So guys, four domains are tetrahedral. What's the angle? 109.5. But Isabel mistakenly said trigonal pyramid. When does this become trigonal pyramid? Yeah, so trigonal pyramid would be, for example, NH3, because you've got nitrogen, hydrogen, 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 unbonded electron domain. So it would be as if you've got you've got a hydrogen there, a hydrogen there, a hydrogen there. That's your nitrogen. And then that is a big, fat, unbonded pair of electrons. And I never know which ones to build ahead of time, so I just build them on the fly. But guys, when we have something like this, we then end up with this structure, which is NH3. And guys, we do not call this trigonal, or we don't call this tetrahedral. We call this trigonal pyramid because we've got the unbonded pair of electrons down here. And then do you remember those push down, and what does that angle become? Less than 109.5. You guys don't need to know, it's actually 107 degrees, but you don't need to know that. You just need to know less than 109.5. Okay, go ahead.
Is it 107 just for an NH3?
Yes, and that's why you don't need to know, is because those angles are not universal, they're approximations. So guys, let's right now, because this is a great time to do it, let's talk about how you're going to communicate the thought process that we just went through to the AP graders. NH3 is too simple of an example, but let's pretend. So guys, pretend that on the AP test, it says, what is the geometry of NH3? Because that's what it's going to say on the AP test. It's going to say, what is the, it could be molecular geometry, but what is the geometry or the molecular geometry of NH3? And the first thing that should jump into your mind is, which one? Do they want to know the domain geometry, or do they want to know the geometry of the actual molecule? Well, if it says molecular geometry, you know which one to pick. But many times it'll just say, what's the geometry? And guys, the answer is this. Regardless of how they ask the question, you will never mention domain geometries. Don't do it. So then you're like, wait, why did you teach us domain geometries if we never get to mention them? And the reason, guys, is because if you didn't understand domain geometries, you might just think that NH3 looks like that and it's trigonal planar. But if we understand that this unbonded domain creates repulsion and forces this thing to be trigonal pyramid, again, tetrahedral domain geometry, trigonal pyramid molecular geometry, then the idea geometries become useful to us, but they don't become something we talk about. So guys, when the test asks you, what is the geometry, they only are thinking about molecular geometry. The domain geometries never come into the conversation. It's just the way we understand it.
So we can't say it's trigonal pyramid?
Well, it is trigonal pyramid.
What's the thing that we can't say?
Tetrahedral. So when you learned this last year, you would have said NH3 has a tetrahedral domain geometry and then a trigonal pyramid molecular geometry, right? So it's tetrahedral because we've got N and H and H and H and this. So last year when you learned this, we would have said tetrahedral domain geometry, trigonal pyramid, molecular geometry. All we're doing is we're not mentioning the domain geometry because that's not a part of the way the AP people think about this. Is that okay? Go ahead.
So when we're going from electron domain geometry to molecular, the thing is you just like take into account which bonds are like more repulsive.
Yes, so it actually summarizes like this. Find this in your book if you want to. So remember the idea. So you've got two domains, both bonding, that's linear. If you've got three domains, the domain, let me write on here, which I can't do right now. But if you've got three domains, then the domain, white's a bad choice. If you've got three domains, then the domain geometry is trigonal planar. If all three of those are bonding domains, then the molecular geometry is also trigonal planar. If two of those are bonding and one is non-bonding, then it's bent. And then similarly here, 4 domains is tetrahedral. If all 4 are bonding domains, the molecular geometry is tetrahedral. If 3 are bonding, it's trigonal pyramid. And if 2 are bonding, it's bent. But the take-home message is the only stuff that the AP folks want you to understand. Yeah, the only stuff the AP folks want you to talk about is that. So we use the domain geometries to predict the molecular geometries. All that they're looking for are the molecular geometries. And guys, the reason is because there are other ways to teach how to get to the molecular geometries. There are people that teach this without teaching domain structures. That's the way I learned it in high school and also in college. I hadn't seen domain geometry stuff until I started teaching AP. I like it better, but it's not the only way. So does that make sense? You guys okay? Okay, so guys, that was all review, right? You guys ready to look over the horizon a little bit? Here we go.
The electron pairs that surround a central atom
I went
are
back
most
to the
likely
same
to be
video.
found in confined regions of space called electron domains. The arrangements of the electron domains about a central atom are determined by the electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time they are held by their attraction for the central atom. When there are 2 electron domains about a central atom, they are located 180 degrees
Linear, right?
apart to minimize repulsions. 3 electron domains about the
Trigonal planar?
central atom take up positions in a plane separated by 120 degrees. 4 electron
Isabel? That a girl. All right.
domains form a tetrahedral arrangement about the central atom.
Okay. So this is last year. You ready for this year?
How does this relate to those shapes?
It doesn't. No, it doesn't. And that's what we're going to talk about. That's what we're going to talk about on Tuesday. Yep. You ready? Here we go. 4 electron domains, tetrahedral.
5 electron domain
Guys, 5 electron domains. This is what is called a trigonal bipyramidal molecular geometry. It could be molecular, but right now it's domain. So this is a trigonal bipyramidal molecular geometry. So what I'd like to do is I'd like to take this opportunity to share with you the terminology and the concepts that you need to understand relative to this. So guys, this is new stuff. So first of all, why do we call this trigonal bipyramidal? And the reason is this. So imagine that you connect these points. We now have a triangle, But if you then connect those points up, you end up with a pyramid with a triangular base. But if you then do the same thing down, you've got a second one. So it is trigonal. It's not bad. This is trigonal bipyramidal because you've got a three-footed pyramid on top and a three-footed pyramid on the bottom. Okay. Now, guys, with that said, let's talk. And this is important that you understand this. This isn't fluff. Guys, what are these angles right here? 120 degrees. What are these angles right here? 90 degrees. Keep that in mind. And now let me share with you a couple terms. Guys, these domains right here are what are called the axial domains. This is maybe something you might want to is you could go trigonal by so trigonal bipyramidal, this is 5 domains. Trigonal bipyramidal has what we call axial domains. You can even get really brave and sketch this if you want. If I can do it, you certainly can. But guys, the axial domains are obviously the domains that are on the axis. Now, if those are the axial domains, what about this one, and this one? They are what are called the equatorial domains. Again, keeping with our globe reference, we've got the axial domains and we've got the equatorial domains. Now, with that said, I should be able to ask you these questions. What are the angles between the axial domains? The axial domains are 180 degrees from each other. What are the angles between the axial and the equatorial domains? 90 degrees. And then what are the angles between the equatorial domains? 120. Now, guys, why is this important? Watch. Let me just write these in. So this is 120. No, it doesn't add up to anything. This is 90. And the 180 doesn't really matter. So guys, here's the question. Which electrons have more empty space around them? Let me say it in the singular. Which domain has more free space around it? An axial domain or an equatorial domain? The axial domains. Guys, the axial domains, no. That's, no, sorry, no, bad. Stop. No, guys, the equatorial domains have more space around them because these equatorial domains are 120 degrees away from 2 domains and 90 degrees away from one of the axial domains. The axial domains are 90 degrees away from 3 domains. They have less free space. So the equatorial domains have more free space around them. The question is, so what? And the answer is this. When we are forming molecules with these things, if we have unbonded domains, they tend to be in the equatorial positions. Why would that be true? Because the equatorial domains are bigger and they want more space. You get the idea? The unbonded electron domains. Is that okay? Okay, and guys, we'll talk more about that in a minute. Okay, so this is trigonal bipyramidal. Here comes 6.
Form a trigonal bipyramidal arrangement. 2 of the electron domains are disposed along the vertical axis. The other 3 are found in the horizontal plane, separated by 120-degree angles. 6 electron domains.
Ha! 6 electron domains. Guys, this is not quadrahedral bipyramidal. This is what is called octahedral. Just a second. So where does the name octahedral come from? Well, guys, imagine if you took 3 2x4s and crossed them like this, and then tried to put like sheeting on the side of it to make it a polygon, a structure. Well, you would have to put 1, 2, 3, and 4. Can you see that? That there's four faces, and then there would be 4 underneath. So guys, this has got 8 faces, and therefore it is called octahedral. Now, the question is, which ones are the axial domains and which ones are the equatorial domains? They are all equivalent. These are all separated by 90-degree angles, and so consequently, we do not have axial and equatorial domains because they're all equivalent. Does that make sense? Okay, so guys, with that said, let's do this. So it sounds like we are comfortable with this stuff, right? We're comfortable with the idea that we need to be able to think about molecular geometries, which are predicted by the domain geometries, but we're not going to talk domain geometries, just molecular. Okay? Now, guys, let's do this. Let's have that same conversation about the... Oh, gosh. Oh, I deleted way too much. So guys, let's have the same conversation about these dudes. So here are the trigonal bipyramidal domain geometries. Let's go red. Oh yeah. Don't call it teeter-totter. They will not give you credit for that on the AP test. So guys, 5 domains. These are the axial. Those are the equatorial. If all 5 of those domains are bonding domains, we have a trigonal bipyramidal molecular geometry. Now, what if we have an unbonded domain? Well, guys, first of all, look at where that unbonded domain is. It is equatorial because unbonded domains are bigger, and they're going to go where there's more space, cutting down on repulsion. So if this is the case, we have got 4 domains, and we call this Seesaw. Now, unfortunately, guys, I have no idea where my atoms are that have 5 domains. I was looking for them between classes, and I just came up empty. You know what, though? They are in your model kits. Oh, they're in your model kits. I was like, it's okay. They can just build these 3rd period. But I can do them for you now. Nope, that's octi. Here we go. So, guys, I'm not gonna hang atoms off of these. We'll just put domains. So guys, here's the idea. So this is trigonal bipyramidal, right? Now, if we've got an unbonded domain, we'll just remove it. And now do you see why we call this seesaw? Because if you put it this way, it's like a seesaw. Don't. No! One's right and the other's not. They're the same on the playground. They're not the same in chemistry. So now, guys, check this one out. What if we have 2 unbonded domains? Well, guys, the idea is this. The first unbonded domain will be equatorial. So will the second unbonded domain. And now we have T-shaped. Okay? So 2 unbonded domains would be T-shaped. Then, guys, if we have a third unbonded domain, that will also be equatorial, but now we're back to linear. Get the idea? So the thing to remember with trigonal bipyramidal structures is that the unbonded domains will always be the equatorial domains, and then you need to know seesaw, T-shaped, and linear. Okay. Now let's go down to the octahedral structures. So guys, in the octahedral structures, yeah, so we understand there is no axial or equatorial in an octahedral structure. But with that said, there is something you need to keep track of. So if all 6 domains are bonding, it's octahedral. Looks like this. Now, what if we've got one unbonded domain? Well, it doesn't matter which one we pull, right? They're all equivalent, so let's pull one off. So now what do we have? A square pyramid. It's got a square bottom and it's got a point, so this is what is called square pyramidal. But now, guys, just a second, this does matter. What about a second unbonded domain? And that second unbonded domain will always be opposite the first unbonded domain. So you won't pull this one, you'll actually pull this one, and now we have square planar. Now, what about below that? What about a molecule that's got 3 bonded and 3 unbonded domains? Those don't tend to exist. So the ones that you need to know are simply the ones that are represented here, and you do need to know their names. Again, guys, you don't have to worry about their domain geometries, just their molecular geometries. Go ahead. Like this? Yeah, so it actually will bend up a little bit, because I can't do that, but you know what I'm saying. These do bend up a little bit because this unbonded pair is shorter and fatter than this, but it still looks like a square pyramid. This is going to be a little smaller than 90 degrees, but we still call it square pyramid. Yeah, Kimmy. Yeah. Yeah, but look at what it's bonded to. Yeah, fluorine is so crazy electronegative that it can even get the noble gases to bond. Yeah, you would never see xenon hexaiodide, because iodine is not, well, be careful with never, but iodine is not electronegative enough to get xenon to share. So you'll notice that all of these guys, like here's xenon, there's xenon. Are there any other noble gas-based ones? No. But it's really fluorine that we use to create those compounds, because fluorine's electronegative enough to even get the noble gases to form covalent bonds. I think so. So, guys, what I'd like to do then, moving forward, is I'd like to draw some Lewis dot structures with you, because while I think you're understanding the logic behind this, the question is, what does this look like when we draw Lewis dot structures? So, guys, let's start to throw together some Lewis dot structures. So just get some clean paper. Let me turn on some lights. And let's fiddle around with these a little bit. So guys, let's do this. SF4. So we're going to draw the Lewis dot structure for SF4. Here's the mistake you're going to make. You're going to look at this and you're going to go, oh, 4. I was about to use the word. Okay, I'll use it. Guys, these things on the outside actually have a name. They're called ligands. It's not a term you need to know, but that's actually the word. Why is that funny? Yeah, no, there. So the term that we use for things bonded around the outside of a central atom are ligands. So it's not a word you need to know, but feel free to use it. But guys, so sulfur's got 4 ligands. And you look at this and you go, oh, 4, that's tetrahedral. No, it's not. So let's draw it. So here's the way to do this. Always assume that molecules are simple until they prove otherwise. So if you were just approaching this to draw the Lewis dot structure, you would do this. So do that. Now that we've got this, we need to count electrons. Sulfur as a group made of oxygen has got 6 valence electrons. Fluorine is a halogen, has got 7. 4 times 7 is 28. Add those up and we get 34 electrons. Now, how many do we already have on the board? 8. So if we subtract 8 from that, that leaves us with 26. We're going to get a bunch of unbonded electrons on this paper, right? Do this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. You don't have to draw dots. You can draw your unbonded electrons as pairs represented by lines. But you'll notice that I did that so quickly that you may have lost count. How many of the electrons did we use? 24. We've got 2 left. What do we do with them and where do they go? Well, guys, they can't go on the fluorines. They're done. So where do they go? Well, they go on the sulfur. Now, we now understand that we are going to have an unbonded pair of electrons on the sulfur. Will it be axial or equatorial? Equatorial. And how do we draw that? Like this. And I'm going to overemphasize it. But guys, we draw it like that. What we are now representing is 2 axial domains and 1, 2, 3 equatorial domains. Do you see it? Now, what would this molecular structure be? Seesaw. 5 domains, 4 bonding, that would be seesaw.
How do you spell that?
Yeah, it's not S-E-A, it's S-E-E. Seesaw.
So I have a question. With other molecules that are like not fluorine too, and like not have fluorine,
Yeah?
how do you know that it's like is it always the central atom that gets it?
Good. So the answer is yes. So guys, bottom line is this. When you're drawing Lewis dot structures, if you have filled up all your octets and you've got extra electrons, they always go in the middle. Yep. So let's hold on. Let's do one more, guys. So let's go XEF4. So again, Xe is going to be in the middle. We are going to play it simple until we find out that's not appropriate. And we're going to place these four fluorines evenly around the xenon. Now we need to add up valence electrons. 4 times 7 is still 28. Interestingly, the first time you've ever done this, it's a noble gas. It's got 8 electrons. We add those up and we get 36. There are 8 on the board. That leaves us 28. So now we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That leaves us 2 unbonded pair of electrons. Guys, I'm going to switch colors. Please don't write this down. What's wrong with that? They've got to be opposite each other. Again, these positions in an octahedral structure are equivalent. But when you've got two, so if you only add one extra pair of electrons, it doesn't matter where you put it. But if you've got two unbonded pairs of electrons, they've got to be opposite each other. And then that would give us the structure, square planar. So guys, that's the new stuff. Thoughts or concerns? Go ahead.
So on the sulfur
Yeah.
I'm just wondering, why does it, so like, I know you just explained like the new like 6 electron domains and how it forms a seesaw.
But it's only 5 electron domains, not 6.
Yeah, the 5 electron domains. I'm just wondering, why would it form the seesaw as opposed to like sort of like, you know, trigonal pyramid, but why wouldn't that form like 4? Like,
I mean, I can show you the model kit again. And this is why we're doing the lab that we're going to do 3rd period and then next week. So we've got this. Is that the right one? Yeah.
I'm just wondering,
So here's 5. So there's 5. Take away 1.
yeah,
Which, not that one. That's axial.
yeah.
There you go. So take that off.
I'm just wondering
And there you
why
got it.
doesn't look like that.
It does.
Well, like, sorry.
It does bend down a little bit. But it's still a seesaw. It's not a very well built seesaw, but it's still a seesaw.
I'm just wondering why it doesn't push them all down equally.
Because it pushes the axial ones down more because they're closer. And it pushes the equatorial ones down less. So if we can show everybody. So it deflects these more because it's closer. It deflects these less because they're further. So what you end up with is a sagging seesaw. Brandon, don't call it a sagging seesaw. But it's literally a sagging seesaw. Is that okay?
So, but I'm just wondering why it's not equal.
Let's just do this. It's this. If you want to talk about anything else, let's do it later. It's this. Go ahead. Oh, so what about double bonds? And the answer is no. So, guys, this is important. I'm going to say no for now. We'll talk more about why later. But you will never see double bonds in these structures that go past a full octet. As a matter of fact, you don't even see double bonds in things that are tetrahedral. And I don't know if you ever put that together last year, but if you ever have a tetrahedral domain geometry, you can't have double bonds. You're going to find out why on Tuesday, but by definition, you can't have these more complicated molecules and have double bonds. Is that okay? And we'll talk more. And actually, Daniel, this is interesting. If you want to, don't do it now because you're going to miss what we're about to do. But page 341, just write that down in your notes. Page 341 actually answers your question. Okay, so guys, we are now ready to wrap this up. Yeah, just go if you need to go. That's fine. So guys, let me, here, do this. Give me 28 seconds. So guys, this is also review. But this is where we're going next. And this is all review. We need to talk about, very briefly, molecular polarities. Let me show you quickly what you need to remember. In order for a molecule to be polar, it has got to be non-symmetrical. So guys, the idea is this. If you look at a molecule like carbon dioxide, this bond is polar towards the oxygen. Why? Because oxygen's more electronegative. This bond is polar towards the oxygen. Same reason. But why is the molecule not polar? It's symmetrical, it's linear, and therefore they cancel out and it's nonpolar. Now guys, here, this bond is polar towards the more electronegative oxygen. This bond is more polar towards the more electronegative oxygen. And the molecule is polar towards the more electronegative oxygen. What is it that makes it polar? It's non-symmetrical. And this bond's going this way, and this bond's going this way, and the overall movement, which is the overall dipole, is towards the more electronegative oxygen. So, guys, let me give you this little nugget, and then we're going to call it a day. Guys, what do you look for to find molecules that are polar? And guys, the answer is this. One thing to look for is unbonded electrons. If you have unbonded electrons on the central atom, there's a very high likelihood that that thing is going to be polar. Simply because those unbonded electrons tend to bend molecules. But guys, that said, here, where'd it go? Here, oh, there it is. That's an exception. This has got unbonded electrons on it, but it would be nonpolar. Why? Because the unbonded electrons balance each other out as well. But it's all a question of balance. If you've got an unbalanced, non-symmetrical molecule, that thing will be polar. So guys, we are going to wrap up there. If you need to go, well, here, let me do this. No. Yeah. So guys, here is your homework. It really is this big. So guys, when I see you after the assembly,